Hello, everyone. My name is Andrew Kim, and today I'll go through the second part of our review session for the RLC circuit. So in the first part, I explained about the basics of circuits, how capacitors work, how resistors work, and stuff like that. I also explained about Kirchhoff's rule and the Jones law as well. And then I started explaining about RC circuit, but I wasn't able to make it to RL circuit or LC circuit. So in this video, it's going to be shorter than the previous one, hopefully. And in this video, I'm going to talk about RL circuit and LC circuit. Now, I believe RL circuit is very similar to RC circuit, so I don't think that'll be a huge issue for most of you guys. However, LC circuit is a bit more complicated, and there are some concepts that you would have to be sure of. So it's going to be a bit more complicated, but I'm going to go through it right now, so don't worry. So let's get started. Okay, so let's go back to the notes that I have over here. RL circuit. Let's get started. So first of all, RL circuit, in order to understand RL circuit, you have to first understand about L or inductor, because R, you already know what it is. It's a resistor. You know how it works. It works under the Ohm's law and everything. You know those things. So the next thing you have to know is what L is, or what inductor is. And basically, inductor, the whole point of inductor, why scientists made inductors in the first place, is because they wanted to prevent a situation where too much current flows at once. What I mean is when you have a disconnected wire and you suddenly connect the wire, the I, or the current, is going to flow in its maximum strength as soon as you connect the wire. You want to prevent that, because a wire that had zero current and suddenly, if the current increases to its maximum point, then the wire or the circuit is going to feel a lot of burden, and that might harm your circuit. That's why we need inductors, which is essentially used to decrease that steep increase in the current. So basically, it works as like a buffer solution, or sorry, no, that doesn't make any sense. It works like, but you know what I mean, right? It works like a bumper in a car, for example. It tries to decrease the amount of sudden abrupt change in the current. So that's the whole point. And that is why when you connect a RL circuit and you have voltage or battery, initially at the starting point, the inductor works as the voltage, the same voltage as the battery you have over here, except this inductor, the direction of the inductor, or the voltage that this inductor makes, would be the exact opposite. So the voltage over here, the battery, would form a voltage towards the current, like this, towards upwards or towards clockwise. However, this inductor over here forms a voltage towards this way, right way, or counterclockwise. So basically, it forms the same amount of voltage present in the circuit, but in a different direction, simply to cancel out the difference in voltage and make it impossible for the current to flow initially. Why? Because that's the whole point of inductors. You don't want a sudden increase in current when you connect the circuit. You want the current to increase gradually. That's why initially the inductors work as the opposite direction voltage to cancel out the voltage present in the circuit and thus make the current zero initially. However, as time goes on, this voltage formed by the inductor will decrease, meaning that the amount of current that can flow in the circuit will increase, but not steeply, not abruptly, not from zero to max, but gradually. So again, at start, the inductor works as the opposite direction battery, but at the end, it's going to work like an ideal circuit, because at the end, now after infinite amount of time, you had enough time for the current to increase from zero to maximum without like a sudden change. So after infinite amount of time, you had enough time for the current to increase, so the current will reach to its maximum point, meaning that the voltage created by inductor would be zero, meaning that it's going to simply work as an ideal circuit without any obstacles, without any elements attached to it. So it's going to work just like a connected wire without any elements on it. And in order to calculate the amount of current that flows on the circuit in any given time, you would have to use this formula, I equals to epsilon over R times E to the power of negative RT over L, which can be simplified to this formula, I0 times I minus E to a power of negative R2 over L. And people might ask, what is I0? Of course, I0 is the maximum amount of current. And then how do you calculate this? How do you calculate the maximum amount of current that's flowing on this wire? Well, again, of course, the maximum amount of current would be the current that's flowing after infinite amount of time, right? Because basically the whole point of inductor, again, is to decrease the amount of current that's flowing initially. And as time goes on, you decrease that voltage created by the inductor to increase the amount of current that's flowing on your circuit. So of course, after infinite amount of time, you would have the maximum amount of current flowing. In other words, the current is at maximum after infinite amount of time flows, and when the inductor simply works as an ideal circuit. So in order to calculate I0, or maximum amount of current that's flowing on your circuit, you simply have to calculate the amount of current that is flowing on this circuit, where you have the same resistor, the same battery, however, zero or no inductor present. Because basically, again, after infinite amount of time, the inductor is going to simply work like an ideal connected circuit. Of course, you need the time constant. Again, I never really use time constant in calculating I's, I0s, and stuff like that. But the only reason why I memorize this time constant is because simply in some MCQs, the questions actually ask, what is the time constant of this given circuit? So for those questions, it's good to memorize the time constant. And in this case, the time constant would be tau equals to L over R. And another thing interesting, and another thing you have to know in order to solve the problems in next type of circuit, LC circuit, you have to know this concept, which is the energy stored in the inductor. Similar to capacitor, inductors also store energy, and that energy you can calculate by the formula. U equals to, U stands for the energy, by the way, U equals to 1/2 Li squared. Once again, this formula looks very similar to the ones we already know, which is the potential energy, Ke or Ek equals to 1/2 mv squared. You can see how 1/2 is the same, and literally mv squared is the same, except the alphabet changed to L and I instead of M and V. Now L over here would mean the inductance of the inductor you have, and I would mean the current that's flowing through your inductor. Now, what you can notice is that when is the current maximum? Well, it's maximum after infinite amount of time when the inductor is simply working as a straight wire, right? So that tells us that after infinite amount of time, your inductor will have more energy stored. Whereas initially you have zero current, meaning that I over here is zero, thus you have zero energy charged on your inductor, which makes sense, obviously, because initially at the starting point, you won't have any energy charged in your inductor, whereas after infinite amount of time, of course, your inductor would be fully charged. So, well, when I say charged, by the way, I don't necessarily mean the charge, the plus, the protons and everything, but I'm just more of talking about energy-wise. Energy is fully charged. So that's one thing you would have to know about RL circuits. Now let's move on to the hardest part probably, which is LC circuit. Now, LC circuit, in fact, is it's similar to something we learned before, which is simple harmonic motion. As I mentioned just now, both capacitor and inductors can work as storing energy, which is similar to simple harmonic motion. If we think about simple harmonic motion, we have two sources that are storing energy. For example, if you look at this image, the two sources would be the spring, or the energy stored in the spring, and the energy on the object in the form of kinetic energy. So you have the two sources of energy that are increasing. If one increase, then the other decrease, and if the other increase, then the one decrease, then the other one would increase. So they're in inversely proportional relationship, and that's exactly the same over here. If you have more energy stored in the capacitor, you would have less energy stored in the inductor, and you have more energy stored in the inductor, then you will have less energy stored in the capacitor. They are in a relationship where they're giving each other energy, making one charged while the other one's not, and the other one charged while the other one's not charged. So that's the relationship they're in. And now one thing important to know is that basically when would the capacitor have the maximum amount of energy? Well, that's when the other energy source, which is inductor, does not have any energy stored in it. So when capacitor have the maximum amount of energy, L, or your inductor, would have no energy stored. Now, what's interesting is that L, or the amount of energy stored in your inductor, is U equals 1/2 Li squared. Now, what I'm saying is that when capacitor has the maximum amount of energy, inductor should have 0 energy, meaning that this formula should be equal to 0. Now, one thing interesting is similar to C in capacitor, L in inductor is a physical trait. It does not change depending on the amount of current or depending on the amount of voltage across the inductor, but it only depends on how physically L or inductor looks like. Thus, L isn't something that can change or become 0, meaning that the only source in this equation that can make 1/2 Li squared into equal 0 is I. So you need to have 0 amount of current flowing in the inductor in order to have 0 energy stored in it. Thus, to conclude, when capacitor has maximum energy stored, inductor should have minimum or 0 amount of energy stored. Thus, there will be no current flowing. Because if there is some current flowing, then 1/2 Li squared, which is the amount of energy stored in the inductor, won't be equal to 0, meaning that the capacitor won't have maximum amount of energy stored. Now, let's think of the opposite case. When would capacitor have least amount of energy stored? Well, that would be when capacitor has 0 amount of energy stored, and that's when the inductor has maximum amount of energy stored. Now, one thing you would have to know is that when the inductor has the maximum amount of energy stored, again, the energy of the inductor is U equals to 1/2 Li squared. Now, if this is maximum, again, L is a constant, it can't change. It's a physical trait of the inductor itself. Thus, in order for this equation to be maximum, I, or current, should be maximum. Thus, when the inductor is fully charged and the capacitor does not have any energy stored in it, I, or the current, would be maximum. So when the question asks, what would the current be when there is no energy stored in capacitor, you would have to think, oh, the question is asking about what is the maximum amount of currents that can flow in this circuit. Now let's think about the middle case. Now then, when what if both of them are half charged? What if capacitor is half charged and the inductor is half charged? Well, in this case, I would be in somewhere middle, in between of 0, no current flowing, and I max, or maximum amount of current flowing. It would be somewhere between. However, questions rarely ask this question. Most of the times, question rather asks in a situation where C is fully charged, L is not charged at all, or L is fully charged and C is not charged at all. So you won't really have to think about these specific cases when you're in middle of the two. However, if you do see these questions, if you do encounter these types of questions, rarely, you would have to use the formula over here. Qt equals to Q0 times cosine the omega t plus phi. And as you can see, this formula basically tells how much charge is charged in your capacitor at any given time. At any given time, meaning that it shouldn't only be the situation where capacitor is fully charged or the inductor is fully charged, but it can be a situation in between, in the middle of those two. So that's why you can use this formula. And also you can see how this formula looks very similar to the formula for a simple harmonic motion. And basically, it's because they're literally the same thing, except for in this situation, everything's happening on an electric circuit, on an LC circuit. Of course, be aware of phi. Don't mess up with phi. Figure out the phase, where the phase starts from. Does this simple harmonic motion start from C fully charged? Does this simple harmonic motion starts from inductor fully charged? Does this the simple harmonic motion start in the middle of the two, you have to first figure that out and then use that information to calculate phi and then put everything inside this formula. However, again, you would rarely have to use this formula, and as long as you understand this simple harmonic motion, how this thing works, and when the current is at its maximum, when the current is at its minimum, when the capacitor is fully charged, when the inductor is fully charged, and everything, as long as you know how the things work, how the things are related, then honestly, you would rarely have to use this formula. And of course, omega is equal to square root of 1 over LC. Now, you will want to use this when you have to calculate the period, because period of this simple harmonic motion, because some questions literally ask how much time does it take for the capacitor in LC circuit to fully charge when it's initially not charged at all. In that case, basically what this question is asking is what is the half of period? So using that, using this omega equals to square root of 1 over LC, you can find the value of half of period. Right. That's it for LC circuit. So we are also going to host a review session. So this was a review video, and we're also going to have a review session where I'm going to go over through some problem solvings and also answer to your questions. So I hope you guys show up to the session as well. I hope my video wasn't too long. It was helpful, and you guys learned a lot from it. Thank you for watching this video, and don't forget to have a great day.